Today we study simple and damped harmonic oscillations. When you study harmonic oscillations, students are worrying about the fact that they have not studied differential equations. So if you study mathematics in advance, then it will take more than 1 year to begin with this simple harmonic oscillations. But we would rather follow a practical way of solving the simple harmonic oscillator and damped harmonic oscillator. So please don't worry about too much. So if you follow my strategy, so it will be very straightforward to obtain the answer. And actually, because you already have studied simple harmonic oscillator in such a way, you already know the uniform circular motion. You are familiar with the solution of the uniform circular motion that is governed by any generic force that has a centripetal acceleration. So we review the uniform circular motion, and naturally the projection onto either x or y direction is the solution identical to the solution for the simple harmonic oscillator. And at the end of this derivation, you will find that the equation of motion for a simple harmonic oscillator is identical to the equation of motion for a uniform circular motion. And you are already familiar with that solution through the previous study regarding the motion on a circle. Okay, so we begin with the uniform circular motion. We already have studied uniform circular motion is the motion of a particle along a circle with the radius r and with constant speed. That means because the radius r is fixed, we have angle theta measured counterclockwise from the x-axis to the radial direction as a constant angular velocity. So theta equals omega t. It is still a uniform circular motion relative to a different reference frame. Here we have chosen the simplest choice, xy axis. We can choose another xy axis. Suppose that this is x prime and y prime. And if we introduce a unit Cartesian basis vector to be E1 and E2 for the x and y axis, we can also introduce a unit Cartesian basis vector for x prime and y prime to be n1 hat and n2 hat. In that case, we can measure this is x prime axis and this is x axis, this is y axis and y prime axis. We can measure the angle from the x prime axis. In that case, we have additional angle delta. So the unit radial vector to a particle on the circle of a radius r centered at the origin will be expressed in terms of radius multiplied by the unit radial vector. And unit radial vector in terms of the Cartesian basis vector along x and y directions are cosine omega t e1 hat and sine omega t e2 hat. As I already stated, we can choose a different coordinate using basis n1 hat and n2 hat. In that case, the angle is measured in a different way. The rate of changing is still the same, but there is a constant called phase constant. So this is a way to describe, simplest way to describe the motion of a uniform circular motion. The unit radial vector rotates depending on the angle, and we have increased the angle by differential d theta, then this becomes theta plus d theta. So even though the name is the same, the actual value of these vectors depends on the angle. If you take the derivative er dot, then because it is completely determined once we know the angle, we can simply use the chain rule. And because this is theta dot, because theta is omega t and omega is a constant, theta dot is omega and the theta double dot is a zero. Because it's uniform circular motion. We know that this one is a unit tangential vector. In a similar manner, we can also find the derivative of e theta. This is er that changes depending on time, that is along the direction of e theta with the rate theta dot. In the case of e theta hat, it changes backward. So this difference is proportional to theta dot, but its direction is along the er hat minus sign. Because of this, we have a fundamental relation for the rotation depending on time. If we repeat the time derivative one more time, we can find the equation of motion for the two unit vectors. Here, er hat dot equals omega. Omega is the theta dot. Theta dot is omega. E theta hat, and because E theta hat dot equals omega er hat minus sign. We can take another derivative. Double derivative is because omega dot equals 0, uniform circular motion. We have E theta hat dot, and using this relation, we have minus omega squared er hat. We can do the same job for the theta, E theta, so double dot, minus omega er hat dot, and that is omega E theta hat. As a result, both of them satisfy er hat double dot equals minus omega squared er hat, E theta hat double dot equals minus omega squared E theta hat. So these are expressed in terms of this. This is a vector equation. This is a vector equation. Double time derivative of radial vector plus omega squared itself equals 0. That is also true for the E theta. Because the radius r is constant in a uniform circular motion, I can multiply r here. And er hat equals x vector, and because r dot and r double dot, both of them are 0, I can change it. Rewrite this one in this form. This is the equation of motion for a uniform circular motion. And if we find a projection onto the x and y direction, what you want to do is take a scalar product to this equation. So E1 hat dot x vector double dot plus omega squared x vector equals x1 double dot omega squared x1. And that is 0. This is true because Cartesian coordinate unit basis vector, its time derivative and its double time derivative are both 0. So we have found that we began with the solution of the differential the equation of motion for a uniform circular motion, the solution. From the solution, we have constructed the equation of motion for uniform circular motion. So what we have done is we have made a projection onto each of Cartesian coordinates. Because it is a two-dimensional problem, I have projected the x component and y component separately, but both of them satisfy the same kind of equation of motion. This is a simple harmonic oscillator. Why don't we multiply mass to this? Because we know Newton's second law of motion. We multiply mass here, mass here. What is mass? This is force. Move this one minus m omega squared x. This is equation of motion, Newton's law of motion. What's that? M omega squared. We set m omega squared equals k. What we find is F equals minus kx. That is what's that? Spring force. Spring's a restoring force. So we have obtained everything. As we have studied previously, the complex number is not complex. It is a very simple. It represents the same points of the two-dimensional plane. One way to describe a point in two dimension is introducing Cartesian coordinates x, y, and it is equivalent to, this is identical. We can use the same real numbers x and y to introduce a complex number x, y, y. They are identical. And this is a complex plane. And x plus iy can be because we can make use of polar coordinates is r cosine theta and r sine theta. Using this, it becomes cosine I sine theta. And we have seen it is e to the I theta. So algebra becomes quite simple. And these two-dimensional Euclidean space and complex plane are identical geometrically. Let's return to the main theme, simple harmonic oscillator of this section. We have derived the equation of motion for the simple harmonic oscillator in two dimensions is exactly the same as the equation of motion for a uniform circular motion. And we rewrite plus m omega squared x equals 0. We scale this mass out. We end up with x double dot plus omega squared x equals 0. That is the equation of motion for the simple harmonic oscillator in two dimensions, and x and y component will be of the same frequency. And here, because the spring constant is identical for any projection, this omega squared is a constant. So k equals m omega squared. or m equals the square root k over m is fixed once you have chosen the spring mass system. And if we return to the original starting point, we began with the solution for the uniform circular motion. This omega determines the period of oscillation, and that is omega 0. Now, let us call this omega to be omega 0. The reason we put a 0 is to extend the theory to the damped harmonic oscillator. In that case, the frequency varies from this original value. So we put this a 0 to indicate that this frequency is for the simple harmonic oscillator. And omega period should be 2 pi if we return to the same phase. So for a sinusoidal function, we have this relation. If we divide this equation both sides, omega becomes 2 pi over period, or 2 pi times the frequency. The frequency can also be written in the form of nu. Finally, we have the answer. This is the starting point. We could have obtained the value without this delta, but in general, choosing the two Cartesian basis vector is arbitrary. So that arbitrariness, that freedom, that degree of freedom is expressed in terms of this base constant delta. We remember that x component depends on cosine and y component depends on sine, and cosines and sine, they are actually the same function except for the translation. This space constant represents the translation between the two functions. Okay, so there are three ways to represent this simple harmonic oscillator's solution. One is to write cosine, and the other is to write in terms of sine, and their linear combination. In any case, they are all a linear combination of sine and cosine. So, one way to describe the displacement of a simple harmonic oscillator is a cosine omega 0 t plus delta. The other is a sine omega 0 t plus something, or their complex linear combination to have exponential I omega 0 t or minus I omega 0 t. They are all equivalent. Let us consider the superposition of a sinusoidal function. Because there are multiple ways of representing the solution for a simple harmonic oscillator, it's better to understand how to transform a representation to another representation. So first of all, we can begin with a linear combination of sine and cosine. In that case, we pull out each amplitude. And each amplitude should, when they are to be added, to have a sine some omega 0 t plus something, or cosine omega 0 t plus something, then we would like to make use of addition formula for sine or addition formula for cosine. In that case, for example, in this case, this is cosine sine sine cosine. This is for the addition formula for sine. Sine sine cosine cosine. That is for the addition formula for cosine. In order to do that, it's good to parameterize the coefficients in terms of cosine and sines. The simplest way is to make use of the fact A over square root a squared plus b squared, b over square root a squared plus b squared. Let's define this alpha and this beta. This alpha squared plus beta is evidently 1. Then we can parameterize the alpha and beta to be cosine theta, cosine delta, sine delta, or sine delta, cosine delta. In such a way, we can make use of the fact cosine squared delta plus sine squared delta equals 1. Okay, so using this identity, we can rewrite the general expression in terms of either sine or cosine. This is the way. First, let us pull out the magnitude. If we multiply outside, we need to divide inside. So this one is a over square root a squared plus b squared, and this one becomes b over a squared plus b squared. In a similar manner, this one is still the same. Still the same. We cannot change this original value. The two difference between the two strategies are this a over square root a squared plus b squared is either cosine or sine. However, if we want to make use of addition formula for sine, then both of them should be positive sine. If you make that's just sine, cosine, cosine, sine. So, okay. But the other case, the cosine, cosine, in that case, we need to put the negative sign on it. So that's the reason why if we use a positive sign in here, this formula has a negative Bay constant. We can generalize this idea to add two exponential functions. If we have two exponential functions, it's good to make use of the fact that a equals 1/2 a plus b plus 1/2 a minus b. And b can be expressed in terms of a plus b minus 1/2 a minus b. We can make use of these two identities to simplify this expression in terms of this. And then this exponential, they have the same argument except for the sign because of these factors. And the common factor represent the first term, they are identical to each other. So using these formulas, we can reorganize the complicated expressions involving sinusoidal functions or exponential function in a rather compact way. So this is a very crucial to simplify the expression for the simple harmonic oscillator. And in the next semester, when you study RLC circuit, electric circuit, you had better make use of these formulas. In addition, when you study wave interference, these identities are so crucial to simplify the expressions. So once you determine the solution for a simple harmonic oscillator, yeah, one of these expressions, cosine with phase, sine with phase, and exponential function with phase. Once you finalize the expression for the solution for this simple harmonic oscillator, what you want to do is to compute the kinetic energy, potential energy, force, and so on. Then you need to take the derivative with respect to time once or twice. This is velocity, and this is for the acceleration. If you make use of this sinusoidal functions, the sign is rather complicated because the cosine derivative of cosine brings in negative sign, but derivative of sine does not bring in the negative sign. So they are a little bit irregular, but you are now familiar with dealing with this kind of calculation. However, if you make use of exponential function, the rule is very simple. Each derivative brings in the I factor, and the factors are identical for any powers of any number of derivatives. Now, let us return to the equation of motion for the simple harmonic oscillator. And why don't we multiply the velocity? Then we can make use of the Leibniz formula for finding the total differential. And you end up with the fact that total mechanical energy is conserved. Using this expression, we can go further to simplify an energy related sum of energies must be the total mechanical energy, that is a sum of the kinetic energy and potential energy that is conserved. So simple conservation relations greatly simplify the computation if you are only interested in the energy. So kinetic energy, potential energy that can be computed by 1 half mv squared and the 1 half kx squared using the solution for cosine, for example. I can compute the potential energy, and using this velocity, I can compute the kinetic energy. We can find magnitude is the same. Sum of these is exactly 1, sine squared, cosine squared. So potential energy is a blue curve, and kinetic energy is a red curve, and sum of them is fixed. So energy, total mechanical energy is conserved in a simple harmonic oscillator. We can find out the solution for the simple harmonic oscillator using a rather different way. So I have corrected typo in here. Total mechanical energy is conserved, and expression shows we make use of this one. We multiply, we divide by this one. To find the relation, this relation. And we have total mechanical energy. E is here. E equals 1 half m omega 0 squared a squared. So A equals 2e over m omega 0 squared. So A is the square root of this. And we can see x dot square is a positive definite. So it can, the minimum value is 0. So range of x is from minus a to plus a. So we have graph. This is 0. This is x, a to minus a. And this is the physical allowed region. From here, we can find this is x, this is x dot squared. X dot squared is a positive. However, x dot is either positive or negative. So the oscillation is like that. And from 0, there's a minus a to a. This is period, or this is period, or this is a period. So from minus a to a, it is a half a period, and from 0 to a, or a to 0, or 0 to minus a, or minus a to 0, they are all 1/4 of the period. So in order to find out the period, we compute this one multiplied by 4, then we compute this one multiplied by 2, something like that. So we just simplify our analysis to restrict ourselves to the case x dot velocity is a positive and find out the multiples. If we are interested in the period only. But in general, this calculation can be carried out for a general x in that region. So from 0 to x equals 0 to somewhere x less than a, then we can find the exact time dependence of the problem. First, we recall the period is 2 pi over omega 0. And from this expression, we collect the positive value for the velocity only. And this is completely determined by x only. And this is a dx over dt, separation of variable. So divide this both sides, then you will find the expression for x only. And then multiply both sides with dt, then you have the expression for the t only. And this is total differential. It's a trivial integral. So this is omega 0 t minus t0, something like that. This is the answer. And left-hand side is if you pull out the over factor a and we rescale it, something like that, then c varies from, so xc equals x over a, that runs from 0 to 1. So between 0 and 1. And this one is a trivial integral that is arc sine. And we can carry out the integration as an arc sine c. And c is replaced with x over a. And finally, this is the answer. We can take an inverse transformation from inverse function. This is arc sine is an inverse function of sine. So x of t is a sine omega t minus t0. Here, this t0 is multiplied through omega 0 to find out the expression for the phase constant. So this is the answer. We don't have to find the solution for the differential equation. This is just this solution can be obtained by simply integrating just a single integral. This is quite simple. A second, let me correct this one. You don't need such a big space. Okay. Next, we consider pendulum. Pendulum problem can also be solved using the similar manner. In fact, we have derived these relations by making use of energy conservation and by taking the time derivative, then dividing both sides with the theta dot, we obtain the equation of motion. Or if we neglect the radius of this, if we neglect this radius, then this one disappears and we obtain the torque equation. if this contribution survives, we have a general physical pendulum equation of motion. Unfortunately, this is not exactly the same as the simple harmonic oscillator. It becomes simple harmonic oscillator only if it is allowed to make an approximation. Sine is the theta minus theta q 3 factorial plus the fifth power 5 factorial and so on. If theta is small enough, they can be neglected. Approximately, in that case, we have a simple harmonic oscillator. However, in general, it has sine theta instead of theta. So this one is not really a simple problem. It involves elliptic integral that cannot be evaluated in a closed form, that can be evaluated only through numerical calculation. Next, we consider damping force. In addition to the simple harmonic motion, and these are already we have already considered the damping force. So let me pass through. Just apply the damping force. Just apply the damping force to simple harmonic oscillator. That is called the damped harmonic oscillator. Damping force is proportional to the velocity, but the coefficient B is positive, so it is against the velocity. So opposite to the velocity. If you damp x dot, then you will find minus b x dot squared. This is a positive, and this is positive, so total is a negative. That means damping force dissipate the energy. Energy is decreasing under the presence of the damping force. The equation of motion is written in this form that when we rescale this equation with m, just like what we have done with the simple harmonic oscillator with characteristic frequency square root to k over m. And we define a new variable, new parameter, b over mass m. This is gamma. So what we're gonna do is to find out the solution for this. Unfortunately, the solution for our previous simple harmonic oscillator does not work in this case because of the presence of this first order derivative term. Let's find out the solution for damped harmonic motion. Here, we introduce a trial solution. We can use this trial solution. If it works, that's fine. But if it doesn't work, we need to think another way. However, why not? Trying doesn't hurt you. So substitute this one in here, and we know for any lambda may be complex number. If you take the derivative, the exponential function brings in the additional factor, but the original shape is the same except for the additional factor. If you apply the derivative twice, then you have lambda squared. Then what you obtain from this equation by substituting this trial solution, the answer is quadratic form of lambda multiplied by the every term after the differentiation or not. Every term has the same factor e to the lambda t. I can factor this out. This factorized the form. However, this exponential function is never zero. It is never zero. Therefore, we can always divide this common factor both sides. This results in the quadratic equation in lambda. This is called eigenvalue equation or characteristic equation. Eigenvalue means this lambda that is a characteristic value. Or eigenvalue. It's German word. Eigenvalue. Quadratic equation is solvable always, and middle school student can solve this. The answer is this. We have a discriminant that is not determinant. Discriminate whether this argument of the square root is a positive, negative, or zero. If it is positive, lambda has a two real values, two real solutions. If it is zero, lambda has a single value. This is double root. If it is negative, then we have a pure imaginary part. The, the, the imaginary part becomes I plus minus I square root omega 0 squared subtracted by 1/2 gamma squared in that case. So the discriminant is quite important. According to the discriminant, it is a negative discriminant, vanishing discriminant, and this is vanishing discriminant, and is a positive discriminant. If the discriminant is a negative, we have minus 1/2 gamma plus minus I something. If it is a positive, your answer is plus minus this. If the discriminant vanishes, your answer is only this, the double root. So if we substitute this one into the trial solution, you will find this is e to the minus e gamma t, and either cosine or sine shape, some constant, the linear combination. So it is oscillating, but it has an exponentially decaying factor. So amplitude is decaying, so we say it is underdamped. This is damping. Next one, there is no oscillation. It is a exponential decaying function only. So we say that damping is a very strong. So that's the reason why it is called the overdamped case. If it is a double root, then only a single root is apparent. So we have to find the second solution. Anyway, it is marginally on the border between the underdamped and the overdamped. That's the reason why we call it critically damped motion. So there are three classes, three kinds of solutions. Let us first consider underdamped motion. That is composed of the real part of the eigenvalue and imaginary part of the eigenvalue. Real part of the eigenvalue determines the decay rate of the amplitude, and the imaginary part of the eigenvalue determines the oscillatory behavior. And the solution is the linear combination of this overall factor is a common linear combination of the sinusoidal function with the angular frequency omega prime. And omega prime, as is stated in here, omega prime is omega 0. I have factored this out. 1 minus 2 omega 0 gamma squared. And this is a positive number, and this is total is positive number. So this one is between 1 and 0. Therefore, omega prime is always less than omega 0. If omega prime is less than omega 0, the original simple harmonic oscillator has this kind of solution, but damped harmonic oscillator has a little bit bigger, the smaller omega. That means period becomes longer. There is a delay. This is called underdamped motion. We have this illustrated. The typical solution is, it is not general, but typical solution gives oscillatory behavior, but amplitude is decaying. So this is red one is for the velocity, and blue one is for the displacement. And as you can see, because of damping power is negative. That means energy of the solution is decreasing. The energy is a total mechanical energy that is for the kinetic energy and potential energy. So this decreasing behavior of total mechanical energy says the energy, that part, the lost part of energy has been moved to somewhere else as a heat energy, internal energy, something like that. So initial total mechanical energy is still here, but the green one is the total mechanical energy of the system. So these are lost to somewhere else. Kinetic energy as the internal kinetic energy of the whole system. Next, we consider overdamped case. Overdamped case has a large damping coefficient, so both of them are positive. But you can see that gamma prime in here is less than gamma. This is this one is between 0 and 1. So gamma prime is less than gamma, therefore lambda plus minus both of them are negative. That means it is strictly decreasing with a little bit different rate, but a linear combination of two different exponentially decaying functions that can be expressed in either in this form or using hyperbolic sine or cosine. This overdamped motion does not allow the oscillation. It is just a strictly decaying shape. And this application is frequently seen at your door damper. It does not allow oscillation. As a result, displacement, velocity, both of them does not show any oscillatory behavior, and its energy is decaying very fast. Next, we consider critically damped motion that is on the border between the underdamped motion and overdamped motion. We know every solution has a real part, but we do not know the other solution other than this solution. So solution is missing. We have to find the second solution. A trick is to introduce this factor and allow the variance in the depending on time of the constant coefficient for the usual case, because this is the only way to find out The only way, a simple way to find out the solution. If we substitute this trial solution, then this relation gives the very simple equation of motion for the coefficient c as a function of time. This is a trivial integral. We can obtain this result by double integration. As a result, the explicit complete solution for the critically damped case is a linear function multiplied by the exponential decaying function. As a result, we can display this result and we can see there is a one simple oscillatory motion up and down. However, after that, there is no oscillation. Oscillation is not allowed in the critically damped motion. Again, there is a plot for the total mechanical energy and the kinetic energy and potential energy. Anyway, this amount of energy is lost. And where is it? It has been transformed into internal kinetic energy of the whole system. That means spring, mass, and surroundings. Because there will be some frictional force, the air frictional force, so the energy is distributed. Okay, we have studied the simple harmonic oscillator and damped harmonic oscillator. Uh, Let us briefly review what we have studied using the subtest. The equation of motion for damped harmonic oscillator is given in this form. Well, the characteristic frequency for this corresponding simple harmonic oscillator is the square root of k over m. And we have substituted a trial solution, whatever lambda, that may be any complex number, and we have substituted and we have made use of the fact the exponential lambda t is non-zero in any case. So we end up with a quadratic equation that is called the eigenvalue equation or characteristic equation. Fundamental theorem of algebra developed by D'Alembert states that any polynomial equation of power, highest power degree, that means degree n, has n complex number when the coefficients are all complex numbers in general. And according to that one, the quadratic equation has two solutions. And middle school students can solve this equation by completing the square, and in some case, it is solved in the real number space, or for example, x squared minus 1 equals 0, x equals plus minus 1. However, if you have x squared plus 1 style, we have plus minus I. So depending on the sign of this constant term, the nature of the solution is determined. If it is positive, then you have pure imaginary part. This is oscillatory motion. And if it is negative, then your solution is completely real. And in general, the two independent solutions can be added with an arbitrary coefficient to set it, and this is called the general solution. This one gives a 0 if you substitute to the equation. This one gives also 0. So whatever number you multiply, this is the general solution. This one gives exact 0 for the equation of motion. Once you know the initial conditions that are the position or the velocity at t equals 0, the C1 and C2, those three parameters are completely determined. Therefore, your answer is a completely determined. In case your solution, uh, we can go further. Why don't we rescale this equation by factoring out the common factor? This real part is completely determined and it is universal for all three cases. So, to simplify our analysis, we redefine the position, the displacement of the harmonic, damped harmonic oscillator, and we define a relative one in comparison with the common factor. Simplifying the equation, substituting this one into the equation, and you end up with a very simple equation, including this. Because again, this exponential is never zero. I can divide both sides, and I end up with the equivalent equation. This equation of motion does not have y dot. Very simple. And you have the three kinds of way: plus one zero style, minus one zero style, or equals zero style. This is double root, and this is for the oscillatory motion that is underdamped case, and this is a real valued solution that is for the overdamped case. Next, we consider the equation of motion for a pendulum in general. We learned that the total mechanical energy conservation gives this relation, and this relation can be used to integrate. You remember what we have done with arc sine for the simple harmonic oscillator. So we use the same trick to find the period. The problem is that the integral is quite complicated. And as you can see, when the denominator touches zero, it diverges. The only way to solve this equation, this carry out integral is a numerical evaluation. There is no closed form formula for this integral table. So we have this kind of systematic change of variables, and you can follow to end up with the reparametrization of the period of a pendulum. And this involves the integral called elliptic integral of the first kind. As you can see, k is this amount, the maximum angle theta zero for the pendulum. And why don't we expand this one? You can see this half a pi. If we substitute half a pi, sine is cos 1. So if theta 0 is less than half a pi, then this number is less than 1. Only if this number is less than 1, we can expand in powers of this number. So we know how to do that. What's that? Binomial expansion. It is not always true, but it is true for a small number that is less than 1. So applying the binomial expansion, I can rewrite this one as a series of sine powers. At the end of the day, it is expressed in terms of factorial function. Right now, it looks very complicated, but later part of this semester, you will have to consider the factorial function to consider the central limit theorem that is very closely related to the uh, entropy problem. Anyway, you don't have to be a master of this kind of calculation. However, So let me just quote the final result. It can be expressed in a series. And these numbers are Wallis number, that results from this interesting integral. Okay, the x is missing here. So I have corrected the typo in here. And finally, the formula, well, by making use of the maximum amplitude in the angle, the period is corrected like that. So this first term is true only for the limit sine theta equals a theta, a very small one. But additional piece will correct it significantly. Anyway, what we use as a pendulum as a clock is due to the efforts of Galileo. Galileo has found that the period is proportional to the square root of length, but finally Christian Huygens found it, and he patented patented in 1657. Anyway, any complicated uh, mathematical function is not a mathematical function, it's about a physical function developed from solving physics problem. That's the reason why we have to study physics to understand better about our own problem. That's it for today. Thank you.